Today is the final lecture about sorting algorithms. So we had 3 lectures about sorting algorithms. Today will be the final one. Today we'll talk about why the sorting actually works in n log n time. So we learned 3 different sorting algorithms. We learned the merge sort algorithm, we learned heap sort algorithm, and quick sort algorithm. And all these 3 sorting algorithms was very different. So we used different ideas, we used different techniques, we used like different codes. One algorithm was randomized. Here we used some heap data structure. Here we used some divide and conquer technique. But all 3 different algorithms work in n log n time. I don't know what's the problem. You again have some problem with Twitch? Oh. Okay. So we have 3 different sorting algorithms, and all 3 different sorting algorithms work in n log n time. Let's think about the following. So is it possible to have sorting algorithm which works faster than n log n time? So and interesting fact that his idea is that it's not possible. So for a sorting algorithm, it's not possible to achieve the faster time than n log n time. Let's talk about why it's happening. To prove that it's not possible to get a sorting algorithm which works faster than n log n time, we need to fix the set of operations we can do with the elements of the array. So we have array of some elements, and to prove that something is not possible, we need to fix the set of operations we can do with these elements. And in these 3 sorting algorithms, the only operation we need is to compare 2 elements. So the only operation we need to get these sorting algorithms is to compare 2 elements. So we need to be able to check if one element is less than another element. If they can compare 2 elements, we can make any of these sorting algorithms. For example, in merge sort, when we merge 2 arrays, we take the first elements of each array, compare these 2 elements, get the minimal one, and move to the next one, and so on. So the only operation we need is to be able to compare 2 elements. The same thing with the heap sort. When you have heap data structure, the only operation you need to do with the elements is to compare 2 elements. So you insert new element, compare this element to the parent element. If it is less than parent element, you swap them, and so on. So you only compare 2 elements with each other. Just checking the chat. Okay. Now, let's prove that if the only operation we can do with the elements is to compare 2 elements, it is not possible to make the sorting algorithm faster than n log n time. How to prove this? It's kind of tricky. So if you want to prove that some problem is not possible to solve with fast algorithms, you need somehow to show that any fast algorithms so somehow you need to show that all fast algorithms do not solve your problem. And how to do this in this case? So this is one of the easiest case. For sorting algorithms, it is known that it's not possible to solve them faster than n log n time. How will we prove this? Let's do it in the following way. Let's see. So, let's build the following tree. For example, let's have 3 elements. Let's say we have 3 elements, x, y, and z. And we want to sort this element in increasing order. And the only operation we can do is to compare 2 elements with each other. So how can we do it? No, let's say, for example, first, let's say we compare x and y. So we compare x and y. Let's see if x is less than y. So if x is less than y, then let's compare x and z. So compare x and z. If x is less than y and x is less than z, then x is the minimal element. Now we know that x is the minimal element, we need to compare y and z. So we compare y and z. If y is less than z, then we know that the minimal element is x, next element is y, and next element is z. So we output this sequence of elements. So this is sequence is in sorted order. If y is greater than z, so it's less, so this is greater. Then x is the minimal element, then is z, and then y. Now what happens in this branch? So if x is less than y, but x is greater than z, then z is the minimal element. So x is greater than z, but it is less than y. So this is the only possible answer. And so on. So in the right branch we have the following. So if x is greater than z, then y, then we compare, let's say y is the minimal element, so we compare y with z. If y is less than z and y is greater than if y is less than z and y is less than x, then we need to compare x and z. If it is less, then we have y, then x, then z. If it is greater, then we have y, then z, then x. And finally, here, if x is greater than y, but y is less than z, what does it mean? Oh, I did something strange. Yes. And here we have z, then y, then x, right? Is it fine? Okay. Looks fine. So this is what's happening with your algorithm. And actually, you can build such tree for any sorting algorithm. So what happens in your algorithm? In your algorithm, it works something like you do some operations, then you make some comparison of 2 elements. So you compare some element AI with some element AJ. So if it is less, you do some operations here. If it is greater, you do some operations here, and so on. So any comparison of 2 elements will create 2 branches. Like if it is greater, we go here. If it is less, we go here. So for any sorting algorithms, we can build a tree like this. Now let's look at this tree. What is the height of this tree? The height of this tree is the number of comparisons you need to make to achieve the goal. So if, for example, if you start from here, you compare these elements, compare these elements, compare these elements, and go here. So the number of operations you make to get here is the height of this tree. Right? So this height is equal to the time of your algorithm. Good enough. It's a little bit too dark in this area, but fine. Now, what is the number of nodes in this tree? Let's look on the leaf nodes. So on these leaves. So we have 1, 2, 3, 4, 5, 6. So these leaf nodes are the different outcomes of your algorithm. So you you run your algorithm, and in the end you can get one of these results. So what is the number of different results you can get after you sorting some array? Any ideas? You're too quiet today. Too quiet. Say something. N factorial, good. So the number of leaves in this tree is equal to the number of different permutations of n elements. So when you sort the array, you can get any permutation of its elements. And we have n factorial different permutations. Right? So now let's calculate the minimal possible height of this tree. So the height of this tree is greater or equal than the logarithm of the number of elements. So we have n factorial elements in this tree. So the minimal possible height is logarithm base 2 of n factorial. Right? Now, what is logarithm of n factorial? It's log of 1 multiplied by 2 multiplied by 3 and so on to n. It's equal just to sum of log I for all I from 1 to n. So it's logarithm of product. It is equal to sum of logarithms. And this sum is big omega of n log n. That's all. So the height of this tree is not less than n log n. Multiplied to some constant, doesn't matter. That's all. And the height of this tree equal to the time complexity of your algorithm. So you cannot. So again, why can't you sort the algorithm faster than in n log n time? Because to sort the algorithm, to sort the array, you need to guess one of the permutations of its elements. And to guess one of the permutations, you need to make at least n log n comparisons. So you can think about it, about the information theory. Yes, it's logarithm of the number of leaves, right? So the height is not less than logarithm of the number of leaves of the tree. Because every comparison here give you 2 branches. So you on each next level you have twice more elements than on the previous level. Once again, you can think about it in terms of information theory. So if you need to guess one of the permutations, you need to guess one of n factorial numbers. And to guess one of the n factorial numbers, you need at least this number of bits of information. And every comparison gives you 1 bit of information. So in order to get all this n factorial information, you need to get at least logarithm of n factorial bits. So this is minimal number of comparisons you can make. No, this is the lower bound actually. Yes, which say that time cannot be less than n log n. Again. Okay, so the number of leaves in this tree is n factorial. So the height of this tree, height is the number of nodes on the path from the root to the leaf. So when you go from root of the tree to the leaf of the tree, so you go here, the number of elements you visit is the height of the tree, and it's equal to time complexity. So when you go to here, you need to make these comparisons of elements. The number of elements is n factorial. So the height cannot be less than logarithm of n factorial. Right? Again, why is it so? So if you make, this is the binary tree. So you start from the root. Here you have one node, here we have two nodes, here you have four nodes, and so on. So on level k, you have 2 in the power of k nodes. If here is k. So if we want to get n factorial nodes on the bottom layer, we need to have the height at least logarithm of n factorial. Yes, we have n factorial leaves. That's right. Total number of nodes may be greater than n factorial, but we have greater or equal. Yes, total number of nodes may be even bigger than n factorial. That's all. Cool. So, we just proved that it's impossible to make the sorting faster than n log n time. But this proof only works when you have some abstract elements that you can only compare each other. If you have something more interesting, so in real problems, sometimes you have not just abstract elements, so you can not only compare two elements, but make some more interesting operations. And in this case, sometimes it's possible to get sorting algorithm which is faster. And first we will learn the following code. So let's say we have array A, and it contains only small integer numbers. So all elements are integers from 0 to m minus 1. And m is some small number. Oh, we need some moderator in the chat. Anyone wants to be a moderator? Cool. Yes, welcome to the club. I think 2 is enough by now. Okay. Okay, now we have array. It contains only small integers. So we have integers from 0 to m minus 1. How can we sort this array faster than in n log n time? Let's see. Oh, it's a new whiteboard. for example, let's say m equal to 3, and we have array A, something like I don't know, 1 0 1 2 2 0 1 1 2 0. Let's say we have array like this, and we want to sort this array. How can we do it faster than in n log n time? Yes, the simple idea is just to count the number of occurrences of each element. So we create array, let's say C and T, and we will just count the number of each value. So we'll count number of zeros, number of ones, and number of twos. How can we count number of elements in linear time? So we just go from left to right, and each time we increment the corresponding counter. So initially we have all counters equal to 0. Now we go from left to right, take this element, increase this counter, increase this counter. Then see the 0, increase this counter, see another one, increase again, and so on. We go from left to right. Each time we see the element, go to this counter and increase the counter by 1. So in the end we'll have something like, so we have 3 zeros, 4 ones, and 3 zeros. 4, 2, 3 twos. Like this. So we can go from this array to this array in linear time. So we just go from left to right, and each time we increment the corresponding counter. So this transformation is done in time n plus m. So n is the number of elements in array, and m is number of different values we can have in our array. Cool. Now, when we calculated the number of each element, how can we get the sorted array? No. Let's create the sorted version of array. Let's say a prime, and just put this number of each value in this array. So here we see we need to get 3 zeros, so we just put 3 zeros here, then put 4 ones, and then 3 twos. And this will be the sorted version of this array. And this transformation is also can be done in linear time. So the total time complexity is linear. So let's write it here. It's called the counting sort. And it's done in linear time. N plus n. Nice. What next? Let's improve this algorithm a little bit. So usually what happens? Why it's plus m? Plus m because we need to create this array, and the size of this array is m. So this array is size m. So we need to at least we need to create this array. And now when we go from this array, if you can create empty array in constant time, you don't need plus m in this transformation. But in this transformation, you need to look on each element of this array. So you have m different elements here, so you need to look on all of them. So you kind of need plus m here. No, time complexity is n plus m. Again, how to go from this array to this array, from array of counters to array to the sorted version of array A. You go to each possible value see what is the number of elements of this value, and create this number of elements here. So you need to iterate all elements of this array, and here you have m elements. It's n plus m. It's sometimes it's important. If m is bigger than n, then sometimes it's important it's plus m. Usually, when you use count insert, n and m are equal, so it doesn't matter. So usually you have like n elements, and each element is from 0 to n minus 1. But sometimes in some strange situations, you may have different values on f, n, and m. And it's important to keep in mind that it's n plus m. So it's linear for both the size of array and the number of different elements. In practice, usually m equals to n. Usually when you use count insert, m equals to n. Because it is used in some different situations, like usually count insert is used when elements of array are indices. So you have indices in the array, and you want to sort these indices. And indices are from 0 to n minus 1, and you have n elements. So that's how it usually works. N plus m is the same as maximum. Yes, that's correct. N plus m is the same as maximum. You can prove it just by the definition of big O. Yes. Oh, n plus m, let's say, n plus m is not bigger than 2 maximum n plus m, n and m. So you just change one of the elements with the maximal one. So this is not bigger than this, and this is bigger than this. That's correct. Okay. I missed what I was talking about. Yeah. Let's improve the algorithm a little bit. So, what happens in real life? So in real life, you usually sort not the integers, but some objects. So each object has a key, which is the integer. So, for example, you have something like you have structs, some item, and the struct have some key. You have int, which is from 0 to m minus 1, and some, I know, data. Something like this. So you have some objects. Each object has some important information here. And you want to sort these objects by this key. So this is the key, and you want to sort these objects using this key. So when you compare two objects, you compare these keys. And here is not very clear. So usually when you make sort, you just compare two elements and then swap them and so on. But in this sort, it's not very clear how to do it, because here we just create this array. Here we lost all information about objects. Here we know only the number of each key of each value. So how to get from this array to this array is not very trivial. So let's see. For example, let's use some letters for each object. So we have object A, object B, C, D, E, F, G, H, I, and J. So we have 10 different objects, 10? Yes, 10. So we have 10 different objects, and these objects have these keys. For example, object F has the key S0, and object C has the key equal to 1, and so on. So we have array of 10 objects, and these are the keys of these objects. Clear enough? And now we want to make array of a sorted array of the same objects sorted by the keys. What is the idea? So let's create 3 different buckets. So we'll create 3 buckets. Bucket for objects with key equal to 0, bucket for the objects equal to 1, and bucket of the objects with key equal to 2. So let's create 3 buckets. And now move these objects into these buckets. So we have object A. Look on the key equal to 1. Huh? Yeah, that's what we want to do. So you will use 3 different buckets for 3 different keys. Array of sets is a little bit too much. We need array of vectors actually, but even this is too much. But let's create 3 different vectors. So we look on object A. Object A has the key equal to 1. So we take this element A and put it into this bucket. Now object B has key equal to 0, so we move it into this bucket. So C moved here, D moved here, E moved here, F moved here, G moved here, H moved here, I moved here, and J moved here. This is J. And now to sort this element, we simply concatenate all these lists. So create the final array A as the concatenation of this. So first we have all objects with key equal to 0. So we move this B, F, and J here. So these are zeros. Now we move these elements A, C, G, and H. And now we move these elements. So here we have the sorted version of the same array. Yeah. That's okay. That's a little bit complicated because here we need to have m different vectors. So here we have m different values, so we need m different vectors. So we need to initialize these vectors. We need somehow to increase the size of the vector. So if we don't know the size of the vector, we need to initialize m different arrays. And each time when we add new element, we need to increase the size of arrays, so on. So it's complicated. But it's still working. So if you have like C++ vectors, you can do it like this. But actually, we can do it even simpler. So how to do it the same thing without creating m different arrays? We can do it in one way. So we can instead of creating m different arrays, we can split the final array into m segments and use these segments as m buckets. So instead of creating 3 buckets in separate arrays, we will create version 2. So we will create the final array of the same size and then split it into 3 segments. So we have first segments of size 3. So here we will put all elements of key equal to 0. Now we have the second segment of size 4, and here we will put all elements of key equal to 1. And we have the final segment of size 3, and here we'll put all elements with key equal to 2. So again, we had this array. We calculated the number of elements with each value of the key, and now we just create this array and split it into 3 segments. And each segment is used as a bucket. So now we just iterate over all elements of our initial array and put these objects into corresponding buckets. So we take this element A, see that key equal to 1, so we put it in the first position of the bucket 1. So we put A here. Now we take the second element B, move it here. take the first element C, move it here, and so on. So each time we take the next element, find the first empty position in the bucket, and put this element in the first empty position. How can we do it fast? Very easily. We just remember the first empty position in each bucket. So we just remember these positions for each bucket. This will be position 0, this will be position 1, this will be position 2. And now we take next element, see its value is 2, so we go to the bucket 2, look on the first empty position in bucket 2, put this element here, and then move this pointer one position to the right. Yes, that will happen because we know the sizes of each. So here we calculated the number of elements with any value of the key, and now we know the sizes of these buckets. So we can reserve this number of elements for each bucket. Yes, you can do it, you can use the previous version, but just reserve the number of elements for each vector. But again, you need to create m different vectors. It's much easier to create one big vector than create m different vectors, especially when m is big. Good. So let's finish this. So we got D goes here, E goes here, F goes here, G goes here, H goes here, I goes here, and J goes here. And in the end, we have the sorted array. That's all. That's how the count insert works. You get the initial array, get the array of counters, get the result array, and then put the elements into corresponding buckets of the result array. That's all. Total working time is n plus m. Good. Now, yeah, let's go here. So we learned how to sort the array of small integers. So if you have array of small integers up to m minus 1, then you can sort them using the count and sort in n plus m time. Is this. Now, what happens if you have a little bit bigger integers? So, for example, if you have integers up to m squared minus 1. Well, for example, if m equal to 3, you have integer up to 8, from 0 to 8. What can be limit of n? It depends on the situation. So if you have only one sorting algorithm, it depends on how much memory you do have. If you need to make it once, then you can use like all your memory to create this big array of counters and so on. If you want to do it multiple times, then again, usually if you want to choose the good number for m, you want this m to be equal to n, because it's n plus m. So if m is smaller than n, then this is bigger, and this is bigger, then you just spend too much time on creating this array. So usually if you want to choose the correct number of m, m should be about the same as n. What I was talking about? This. So if the numbers are up to m squared, what can we do? Not all elements, but no, we don't assume that all elements are at least once. So some element may be so, but m squared may be greater than n. That's fine. So some elements are not in the array. What can we do? We can do the following. We can split each element into two parts. if you have some number from 0 to m square minus 1, you can split it like this. You can say x equal to, let's say, y multiplied by m plus z. And both y and z are from 0 to m minus 1. That's like if you're using if you use the how's it called? I don't know the correct term in English, but if you use the arithmetics of base m, then you have two digits integer. Like if, for example, if m equal to 10, so what we're doing here is just split the number into two digits. So we have numbers from 0 to 99, and this is just split into the number into two digits. We have higher digits and lower digits. Okay. And now we will take all integers in our array and split each integer into two parts. So we'll take the array A and split it on, let's say, array B multiplied by m plus c. And now, instead of sorting the big integers, we will sort the pairs of small integers. So, when we need to compare some value and value j is the same as if we compare the pairs. So we compare pairs bi, ci, and pair b, j, c, j, like this. That's all the trick. So now instead of one big number, we have two small numbers. Again, let's show. So, for example, you have, if you have m equal to 10, m equal, no, let's have some array here. Let's have again m equal to 3. And we have array A of elements up to 8. Yes, so we have, let's have something like 6, 2, 4, 1, 7, 2, 3, 4. 8. Good enough, good enough. So we take each number from this list and split it using this technique. So what is 6? 6 is 3 multiplied by 2 plus 0. So we take this and replace it with the pair 2 and 0. Now this 2 is 0 multiplied by 3 plus 2. So this 4 is 1 and 1. This is 0 and 1. This is 2 and 1. 0, 2, 1, 0, 1, 1, and 2, 0. Now, instead of sorting these integers, we will sort these pairs. we sort the pair by the first element and then by the second element. Again, here, when you compare two pairs, you compare the first element. If first elements are equal, then you compare the second elements, like usual. When you compare two pairs, you compare the first element and the second element. Good. So now, how to sort this array? Look again, we need to sort this array by the first element and then by the second element. So the first idea is to make count and sort twice. So sort by the first element and then sort each block by the second element. So the first idea is to make like 3 blocks. Here put all elements with first element equal to 0. So first 0 and something put here, 1 and something put here, and 2 and something put here. And then sort each block. But if you do it like that, you will get this plus m in all these blocks. So here, if you have some, let's say we have n 0 elements here, and 1 elements here, and 2 elements here. So what will be the time complexity of all these sorting? So to sort this array, you will need n0 plus m operations. You will have n1 plus m operations here and n2 plus m operations here. And this plus m ends up to all the time complexity of each block. So total time complexity will be like sum of all these n's will be n plus m squared. That's not what you want. So instead of doing it like this, you can improve it to work in n plus m time, but it's complicated. The easiest way to solve this problem is to do the following. Let's do it in the opposite order. I'll just erase this. Is what m squared, because we have m blocks and we have plus m for each block. We have m blocks and we have like n0 plus m, n1 plus m, and so on, and m minus 1 plus m. And this plus m adds to the complexity of the counting sort for each block. So we have this plus m times, so it will be m squared. So what is the correct approach? The easiest approach is to do the following. We'll do the count and sort twice. First time, we'll do count and sort using the second element as a key. So first we'll sort the array by the second element and then by the first element. So let's see. So we make a count and sort, and we sort these pairs by the second element of the pair. So we look on these second elements and make the count and sort. How can we make count and sort? Like before, we create the rate of the counters. Count the number of each key. So we have 0, we have 3 zeros. We have 1, 1, 1, 1, 4 ones, and we have 2, 2, and 2 twos. Looks fine. And now again, what we can do? We create the same array, split it into 3 buckets. We have bucket of size 3, bucket of size 4, bucket of size 2. And put these pairs into these buckets. So we have 2, 0, put it here, 1, 2, put it here, 1, 1, put it here, 0, 1, put it here, 2, 1, here, 0, 2, here, 1, 0, 1, 1, and 2, 0. So here we have the same array sorted by the second element of the pair. Yeah, that's right. We'll use stability. And now we make again the counting sort, but sort these pairs by the first element of the pair. So we look on the first element of each pair and make the counting sort again. So again, we create an array of counters. Count the number of each keys. So we have 1, 2, 3 zeros again. Okay. We have 1, 2, 3 ones, and we have 1, 2, 3 those. Okay. Stability. Okay. So what happens now? We create the same array, split it into 3 buckets of size 3. Yeah. So we have 3 elements here, 3 elements here, 3 elements here. The preferred required to handle. And now we put these pairs into this new array. Again, we go from left to right and put each pair into corresponding bucket. So we take this 2, 0 into bucket 2, 1, 0 in bucket 1, 2, 0 in bucket 2, 1, 1, 0, 1, 2, 1, 1, 1, 0, 2, and 0, 2. That's all. And now we have a sorted array. Why this array is sorted? Now, should one move together 0, 2? Yeah, 0, 1 is here. 0, 1, 0, 2, 0, 2. Don't get what's the question. Here we sorted elements by the second element of the pair. So here we have elements of second element equal to 1, and here element second element equal to 2. So 0, 1 goes here and 0, 2 goes here. So we sort this array by the second element of each pair. Okay, why this array is sorted after the second iteration of the counting sort? Because these elements are sorted by the first element. Elements sorted by the element. So this array is sorted by the first element of the pair because we just sorted it by the first element of the pair. And in each bucket, all elements are sorted by the second element of the pair because the counting sort is stable. What does it mean? It means that in this bucket, all elements go from this array in the same order we have them in this array. So if we have element 1, 0 and 1, 1, then 1, 0 goes from here, and 1, 1, let's see here, goes from here. So these 3 elements goes from these 3 places of the previous array. And in this array, these buckets was sorted in increasing order. So first we'll have all elements from this bucket, then all elements from this bucket, and then all elements from this bucket. So first we'll have all elements with the second key equal to 0, then we'll have all elements with second key equal to 1, and then from the second key equal to 2. So inside each bucket, the pairs will be sorted by the second element of the pair. That's all. So here, after 2 iterations of the counting sort, we'll have the sort array of pairs. That's all. So what will be the total time complexity? So we have 2 iterations. Each iteration works in n log n plus n time. We have n plus m here and n plus m here. So total time complexity will be n plus m. Home task. You can submit home task. Yes, we'll have discussion tomorrow. Yes, you can submit the home task till tomorrow morning. I think even any time before the stream it will be good enough. will it be fast? What happens in practice? Will it be faster than the usual sort or not? It depends on what situation you have. So in practice, things are a little bit different. Sometimes even the algorithm which have worse time asymptotics on practice may work even faster than algorithm with bad asymptotics. So this algorithm is good in theory. In practice, it's not usually the best way to sort the arrays. It's a good way to sort it when you have very big number of n, very big number of m. So if you have pretty small number of n, m, then it's usually not good enough, because you need to create another array, so you need to spend another memory for this array, and then you need even two arrays. So you need an array of counters, you need the resulting array, so you have to create these two arrays, spend more memory, and then the caching is not very good, because you need to put elements in some random points of this array, so it's not very good for caching. So in practice, usually it's not the best algorithm you want to use. But in theory, it means that you can, the idea that sometimes you can sort the array in linear time, it's good. So in some algorithms, we will use the technique that we can sort the array in linear time instead of in log n time. Now, in practice, it can be good. So you always need to check in your situation what is better. If n is, I think for n up to a million, I think for n about a million, it will be faster than standard sort. Not checked. No, by my intuition, I think is if for n and m about a million, it should be a little bit faster than the standard sort of C++. I think. Not sure about this. No, if you're interested, you can make some experiments. So you can implement this, get the standard C++ STL sort, and then compare them for different values on n and m, and see when one sort is better than another sort. So programming is experimental science. So sometimes you just need to experiment with different practice approaches. And the final thing I was talking about is what happens next. So we just cheated a little bit. So we say if we have numbers up to m squared, then time complexity is still n plus m. And it looks like the time complexity is the same. So when we have numbers up to m, we have time complexity n plus m. Now we have m squared, and time complexity is still n plus m. So it looks like we can just put any number here, and it still be n plus m. That's not exactly the true, but let's see. What if we have numbers up to m, say, in power of k? Then we can do the same trick, but we need to run counting sort not 2 times, but k times. So we split each integer into k parts, like in k digits, and then make k iteration of counting sort to sort these vectors of k digits. So total time complexity will be multiplied by k. So total time complexity will be k multiplied by n plus m. So if you pick this k big enough, you can actually have big time complexity, because just this k will be multiplied by the time complexity of the counting sort. Okay, this whole method called the Radix sort. Let's put it somewhere here. It's quite important method for the algorithms we will discuss. Maybe not quite soon, but at some point we'll discuss some algorithms which will use Radix sort as the important detail. I think it should be enough for today. Should we discuss something more? Actually, we delayed a little bit. There is one more thing I want to discuss actually. You're still here? Okay. One more thing I want to discuss is the sorting networks. Yes, if you learn how to make a suffix array, that's when we used the Radix sort. Okay, the last thing I want to discuss about the sortings is about sorting networks. Let's talk about sorting networks a little bit. So what is a sorting network? Imagine you want to sort an array, but you have a little bit different computational model. So the only operation you can do with the array is to compare two elements and swap them. So we have operation, let's say CMP of I and j, and it runs as follows. So we say if AI is bigger than AJ, then we swap these two elements, I and A. So imagine this is the only operation you have. So you have like the only access to the array is to call this comparator. This comparator will compare two elements, and if they are in the different order, it will swap them. And you want to make the sorting algorithm using only this operation. You're not allowed to do anything but to call this operation multiple times. How to create sorting algorithm which use only this operation? Well, for example, let's say you have 3 integers. Like you have array of size 3. Let's implement, for example, insertion sort. How to make the insertion sort? Again, you have 3 elements. If you want to make insertion sort, then first you compare these 2 elements, and if second element is less than the first element, you swap them. Let's say 1, 0, 1, and 2. So first you call CMP from 0 and 1. And now you need to insert the element 2. So first you compare 2 with element 1. First CMP of 1 and 2. And then you compare, if it is less than element 1, you will move it to position 1. And now you need to compare it to position 0. So you need to call CMP of 0 and 1 again. Okay? So this program will sort the array of 3 elements. Cool? Usually, instead of writing this program, because this program is too simple to use to main instead of writing this program, there is a much more visual representation of this program is to create this scheme like this. So let's say we have 3 elements, so these 3 elements will be like 3 lines. So this will be the element A0, this is A1, and this is A2. Here the time goes from left to right, and each comparator is drawn like a arrow from one element to another. So here we compare 0 and 1, so we call it like this. Now we compare element 1 and 2, draw it like this, and now again we compare element 1 like this. So this is the insertion sort of 3 elements. Nice. Now let's draw, for example, let's draw the insertion sort for something bigger. So let's say we have, let's say we have 5 elements. Let's see how the insertion sort works for 5 elements. So when we have 5 elements, first we compare this element, then again we have second element, we compare it here, we compare it here. Then we have third element, we compare the second element, then here and then here. And then we have fourth element, we compare it here, 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 and here. So this is the insertion sort for the array of 5 elements. How to analyze the complexity of the sorting networks? There are 2 parameters we want to optimize. First parameter is the number of comparators. For example, in this in the insertion sort, the number of comparators is n log n. So the number of these arrows when we call this comparator is n log n. Another property we want to optimize is the depth of this network. So we want to optimize the width of this network. To optimize this, we will allow concurrent calls of different comparators if we can, if they don't interact with each other. For example, if you want to call comparator twice, you call comparators for elements 0 and 1, and then call comparator for elements 2 and 3. These 2 calls do not interact with each other. So this call only uses elements 1 and 0, and this call only uses elements 2 and 3. So we can do them simultaneously. So we'll call this comparator and this comparator using different processor cores. So if you have, for example, multi-core processor, you can do it in different threads of your program. So you can make 2 workers. One worker changes these elements, another worker changes these elements. Cool. Now, how will we change this scheme if we are allowed to make simultaneous calls of different comparators? So let's draw it like this. Again, first we have this comparator, and then we need first this comparator. And now we can make these 2 comparisons, this and this. We can make these to call these 2 comparators simultaneously. So we'll, in one operation, we'll call this comparator and this comparator. So in a line. Now we call this comparator, and now again we call this comparator and this comparator. We can call let's use another mark. We can call this comparator and this comparator simultaneously. So I'll just take these two comparators and put them here. So 3 and here. And so on. Now we take these two comparators, put them here. This comparator put here, and this put here. So this is the same sorting networks, but here we allow multiple comparators to be called simultaneously. Okay, let's see what is the depth of this network. So let's calculate the number of concurrent calls in this situation. And the number of concurrent calls we need to make is about n. It's like 2n, about stuff like that. Let's say big O of n. So we have n squared. No, let's see. So we have n squared comparators, but if we allow to call multiple comparators simultaneously, then the total like time complexity, it's not time complexity, but it's like concurrent time complexity, something like that. So total number of concurrent calls will be up to n. So these are the two parameters we want to optimize. We want to optimize the number of different comparators and the total number of these concurrent calls. Cool. Okay, the final thing we'll discuss today is how to make better concurrent, better sorting network for this computational model. Okay. First of all, it is possible to make sorting network which uses n log n comparators and have depth up to log n. But this algorithm is too complicated and the constant is too big. It's not for practical use. So we will discuss a little bit different algorithm. It's not that optimal, but it's much better than typical insertion sort. T? No, it's T some. No, just some regular T. Let's go. First we'll prove some small theorem. The small theorem is like this. If the sortion the theorem is like this. If you have the sorting network, and it sorts any array of zeros and ones. Network any then it sorts any array. So it's the only property we need for the sorting network to sort any array is to be able to sort any array of zeros and ones. Let's prove this. So, let's say, for example, we have this sorting network. So we have let's say we have like 5 inputs. Then we have some sorting network. Here we have 5 outputs. And we know that this sorting network sorts any array of zeros and ones. Let's see. let's prove that the sorting network sorts any array. Let's see. So let's look on the input array. So here we have some input. Let's look where is the minimal element of the array. For example, let's say minimal element is here. Let's prove that this minimal element will be in the first position after array is sorted by this network. How to prove this? Let's look on the following array of zeros and ones. Let's have this array of zeros and ones, all position equal to 0 or equal to 1, but this position equal to 0. Again, here this array is the input array, like x6, 2, 4, 5. So let's take the minimal element of the input array and make another array of ones and zeros with all elements equal to 1, but this minimum equal to 0. So this array will be sorted by this sorting network. So after the sorting procedure, we'll have array 0, 1, 1, 1, and 1. So this 0 will be moved by this network to this position. So this 0, starting from here, it will go somewhere in this sorting network and go to this position. But this minimal element, this one, when we sort this array, we'll use the same path, because each comparison in this array is the same as in this array. So this one will also use the same path and go into this position. Okay? So we proved that the minimal element will go in the first position in the result array. Now let's take the next element. So next element is like 2. Let's prove this 2 will go on the second position. How to prove this? Let's make another array with zeros on position here and position here. So when we sort this array, this is the array of ones and zeros. So it will be sorted by this network. So we will have this array. Now, in the second array, the comparison between these elements and all other elements are all the same. So these two elements are less than all other elements. So these two elements will move to the same positions as these two zeros. So we will have 1 and 2 in the first two positions of the result array. But we already know that 1 will be on the first position. So the only position for 2 is the second position. Again, first we proved that 1 will be on the first position. Then we proved that 1 and 2 will be on first two positions. So 1 is here, so 2 must be here. And so on. Each time we take the next element, build the array of ones and zeros, show that these first elements must be on these first positions, and we already know the positions of this element, so for the next added element, the only position is this next position, and so on. Is it clear enough? So next, I cannot count, so this must be free. Yeah. So next we will prove that this free, if we remove this one and say 0, so we'll prove that 1, 2, and 3 must belong to these three positions. So we know 1 and 2 are here, so this 3 must go here. And so on. Then we take this 4, prove that it must be here, take this 5, prove it must be here. So we prove that this array will be sorted by this sorting network. Sorry. Oh. Okay, the final step. Now we'll make the correct binaries, the correct sorting network. To build the optimal sorting network, we'll use the sorting algorithm which is called the Bitonic sort. Bitonic sort. Bitonic sort is kind of special algorithm which is used in different situations like that. It's used mostly for some parallel algorithms. I don't know. I know some different topics when used by Bitonic sort, and they all around some parallel stuff. So let's. What is the Bitonic sort? So, what is the Bitonic sequence? Bitonic sequence. Let's have array A, and it is Bitonic if it looks something like that. So it must be something like that. So there is some interval when the array is increasing, and some intervals when array is decreasing. And if we look on the cyclic shift of this array, so if we just take this decreasing prefix and move it here. So this is the array, and when we just move this prefix here, then here we will have the decreasing segment. So if we look on the array like on the cyclic sequence, it should be split into some two parts. One part is increasing, another part is decreasing. Like here, we have increasing part and decreasing part, and it is like cyclic sequence. If you have array like this, it is the Bitonic array. That's all. So Bitonic sort is the special sort which sorts the Bitonic sequence. Bitonic sequence can be sorted in some special algorithm which is called Bitonic sort. Cool. So now we'll create the sorting network which sorts the Bitonic sequence. Nice. Well, for example, let's write some Bitonic sequence. For example, we have array A. So we have some decreasing part, let's say 3, 2. That's good enough. So now we have some increasing part, let's say 4, 6, 10, 25. And then decreasing part like 17. And should be decreased up to this 3, so it's 17, I don't know, 11, 6, 8, 6. So that's the nice Bitonic sequence. So we have this part from 2 here. So here we have less. So here we have the increasing part, and here we have greater. And if we put this 3 into here, here we will have the decreasing part. So this is the Bitonic sequence. Only one. We should have only one increasing part and only one decreasing part. That's why we Bitonic. So what was 1 and 2. Cool. Now we will build the sorting network which will sort the Bitonic sequence. To sort the Bitonic sequence, if we build in the sorting network, we only need to be able to sort all the Bitonic sequences of zeros and ones. What is the Bitonic sequence of zeros and ones? Bitonic sequence of zeros and ones. So if your sequence only consists of zeros and ones and is Bitonic, it looks something like that. So we have, let's say we have some array of zeros, and here we have some segments on ones. So it always looks like this. So we have like all elements equal to 0, and in the middle we have some elements equal to 1. Or the opposite. Or we may have all elements equal to 1, and in the middle some segment equal to zeros. So it's one of these. So Bitonic sequence looks like this. How to sort this array? I have not enough space on this board, so let's erase this. Let's erase everything. Just sort of is not enough. So you need just to sort the array. You need to find the minimal value, and to find the minimal value, you need to run this comparator. We're working in this special model when this is the only operation we can make. And to rotate the array, we need to find the minimal element, and we can find the minimal element because this is the only operation we have. Yes. Yes. In the usual computational model, you can just find the minimal element and then rotate the array and then merge these two parts. Yes, you have one increasing part, one decreasing part. You can just use the merge sort to merge these two parts into one array in linear time. But here we work in this special model. Here we're building not the usual program, but we're building the sorting network. Yeah. So we cannot just make arbitrary stuff with these elements of the array. The only operation with elements we can make is to call this comparator and to compare this element and swap them. This is the only operation we have. Okay. Now, how to sort the Bitonic sequence? Bitonic sequence. Imagine we have array of size equal 2 in the power of k. Let's do the following. Let's split this array into two parts. Let's say we have left part 2 in the power of k minus 1 here and 2 in the power of k minus 1 here. And now we'll call the comparator for each pair of elements here. So we'll compare first element of this part with first element of this part. Call this comparator. Now we call this comparator. Now we call this comparator. And then call this comparator. So we compare each element of the left part with corresponding element of the right part. Well, for example, let's have some array of length 8. So we have some 0, 0, 0, 1, 1, 1, 0, 0. So we have array like this. After we run this on, so we have, let's through. We have like 0, 0, 0, 1, 1, 1, 0, 0. So after we run these comparators, we will have array like this. So we compare. Let's draw everything here. So we have here the first part, the second part. Now we compare this element with this element. They are in the good stage. So this element is less than this element. So we don't swap them. Now we compare these elements, and so on. The only elements are in the bad state are this one and this. So when we have this one compared to this 0, this one is greater than the 0, so we swap them. So in the end, we'll have something like 0, 0, 0, 0, 1, 1, 0, 1. And the interesting property is the following. Now, I want to prove the following. I want to prove that after I make this transformation, I will get two halves. Each half is a Bitonic sequence, and all elements here are less or equal than all elements here. So let's prove the following. So let's prove that both are Bitonic. So this is Bitonic, and this is Bitonic. And all elements here are less or equal than all elements here. Like in quicksort. So in quicksort, we split the array into parts, and all elements in the first part are less than all elements in the second part. Well, let's prove this. So what happened? Let's see. Again, we have some array. We split it into two parts. This array is Bitonic of zeros and ones. So it is some array of zeros with some segment of ones. Let's look on where is the segment of ones. If the segments of ones is in one half of the array, then after the sort, after this operation, we will have here, we'll compare these ones with these zeros. So this array of zeros will move to here. So we will have these zeros here. Oh, these ones will be here. Cool. So if this segment of ones is in the one half of the array, then in the end we'll have one part full of zeros and another part with this segment of ones. Now both halves are Bitonic, because this array of constant, this array is Bitonic. So we have two halves, each half is Bitonic, and first half is less or equal than the second half. Now, if this segment belongs to both halves, so if we have segment like this, so if we have segment like this, then what happens? Then we'll compare these ones, these zeros. So these ones will move to these positions. So we'll have these ones here, and these ones here. And now again, both halves are Bitonic, and this half is less or equal than this half. Here we have only zeros, and here we have zeros and ones. I lost the signal. Cool. And finally, if we have many ones here, so we have a big number of ones, then these ones will be compared to these zeros and move to the right, and these ones will stay in place. So in the end we'll have this part full of ones, and here we have ones in the middle. And here again we have both parts are Bitonic, and these halves are, all elements are less or equal than elements in this half. That's all. Now, this operation split one Bitonic sequence into two Bitonic sequences. Let's call it recursively on both Bitonic sequences. So we have two Bitonic sequences of size 4. Let's do it the same. So let's split each half into two parts of size 2 and do the same trick. So we have these two halves. let's compare this element to this element, this element, this element, this, and this. Now we'll get 4 Bitonic sequences of size 2. And now again, we have Bitonic sequence of size 2. We will split it into 2 Bitonic sequences of size 1. So we call this comparator, this comparator, this comparator, and this comparator. No, here we have 2. I want to claim that this half is Bitonic and this half is Bitonic. The whole array is not Bitonic, but this part is Bitonic and this part is Bitonic. Yeah. So the idea of the algorithm is to split the Bitonic sequence into 2 Bitonic sequences of smaller size, and so on. That's all. That's the whole algorithm. So how many comparators do we need? So on each, so we have n logarithm iterations. Yes. On each iteration, we have n comparators. So the total number of comparators is n log n. Here we have n log n comparators. And what is the depth of this network? So what is the total number of concurrent calls? Let's see. On each step, all these comparators can be run simultaneously. They don't depend on each other. So we compare these elements with these elements. All these 4 comparators can be run simultaneously. So we need one concurrent run here, another here, and another here. So the total number of these concurrent calls will be log n. This number of iterations is log n, so total number of these concurrent calls will be log n. Yes. If we can run comparators in parallel, then this will be number of these parallel runs. That's all. That's how you sort the Bitonic sequence. But how to use this sort when you need to sort some arbitrary array? So, this is how you sort the Bitonic sequence. But you need to sort some arbitrary array. So you given some array, and you need to sort it. This array is not Bitonic usually. So how to sort the array which is not Bitonic? Well, you can do it using the following techniques. So imagine you have some array again of size 8. So you have some 8 elements. 8. So you have some array of 8 elements. How to sort this array using Bitonic sort? Let's look. Let's have each pair of elements form some small Bitonic sequence. So let's call this Bitonic sort to sort the arrays of size 2. And we will sort this array in increasing order, and this in the decreasing, this will be increasing, this will be decreasing. So we make pairs of elements and sort each pair. Now we will look on each 4 elements. So look on these 4 elements and these 4 elements. These 4 elements form some Bitonic sequence. So we can call the Bitonic sort to sort these 4 elements. Now we sort these 4 elements in increasing order. And then call the Bitonic sort to sort these elements in decreasing order. And now we have the whole array is Bitonic, because we have in the whole array we have some increasing sequence and then decreasing sequence. So the whole 8 elements are Bitonic sequence. So we call Bitonic sequence on the whole array and sort the whole array in increasing order. Oh. So this is how you sort the given array. So you're given some array, you split the array into single elements, call the Bitonic sort to make the arrays of size 2, then call the Bitonic sort to make the arrays of size 4, then call it again to make arrays of size 8, and so on. So after logarithm of calls of Bitonic sort, you will get the sorted array. So each call is the call of Bitonic sort. So you have log n calls of Bitonic sort. So the total complexity will be, in total, you will have n log square comparators. And the total depth will be equal to log square, because you have logarithm iterations. On each iteration, you call the Bitonic sort. The depth of Bitonic sort is logarithm. So you need to make logarithm times depth of logarithm. So total depth will be log square. That's all. Any questions? Why these elements are Bitonic? Because any two elements forms Bitonic sequence. If you take any array of size 2, is Bitonic. Just by definition of Bitonic sequence. So you can take any two elements, like see, 5 and 2. So here is greater than this. So you have here you have segment when it is increasing, and here and decreasing. And here you have the segment what is increasing. So any array of two elements is Bitonic. So here you have any pair of elements, it is Bitonic, you call Bitonic sort, sorted elements. Well, Bitonic sort of two elements is simple, just one comparator. Just compare these elements and put them in the correct order. Here you call Bitonic sequence of size 2 and Bitonic sequence of size 4 and so on. Okay, I think it's all for today. Sorry for delay again.